Hello everyone, welcome to this video on classical mechanics. In this video, we shall again see an application of Lagrange's equation, and in particular, we'll see the example of a bead which is sliding on a rotating wire. So we have to find the equations of motion of a bead which is sliding on a uniformly rotating wire in a force-free space. So now this is the only thing that is known to us, and we are interested in finding the equations of motion for this system. So first step would be to visualize what they are saying. They are saying there's a bead and it is sliding on a uniformly rotating wire. So we have this wire like this, and there's a bead over here. This bead can move up and down this wire while this is rotating. So suppose it is rotating about this point. So at one point it is like this, at another point it may be like this with bead somewhere here, and so in some other time it would be something like this with bead over here, and so on. So basically if we can visualize it in a plane, that means this rod represented by this red line, this rod can move about this point origin in a circle, and suppose at some time period t this bead is present at the end of this rod. That means this bead, obviously this bead can move up and down this rod. As the rod moves, the position of this bead differs, but we say the other end of this rod is creating a circle of motion like this. So now we have to select the generalized coordinates which can represent independently the complete system of the complete information about the system. So I can choose r and theta to be the generalized coordinates, where theta is the angle which this rod makes with x-axis, and what is r? R is the distance of this bead from the origin. So now next step is to look at the constraints. What constraints are involved with us? First constraint is that in question you must have noticed we are given a uniformly rotating wire. That means the motion associated with it, that is a uniform motion. So for uniform motion we say the angular velocity theta dot, that is constant. So theta dot is equal to omega, where this omega is constant. We can take any other variable instead of this omega. And moreover, when you so what kind of constraint is this one? Theta dot is equal to omega. This is a holonomic constraint, because if you integrate this, you will get theta is equal to omega into t plus some other constant. So now this constraint also depends upon time, so this is also a rheonomic constraint. So we have two constraints for this. So now because theta, the derivative of this theta with respect to time, that is equal to constant, that means the angular velocity is constant. So let us see how this affects the motion of the bead in a rotating wire. So after having decided all these parameters, the next step would be to find the kinetic energy. And we all know the formula to calculate kinetic energy is that it is equal to half mv square. Now how do we calculate this when we are given the polar coordinates? Now as you can see over here, the coordinates are r and theta. So can I define this position vector r, this as xi cap and yj cap, where what is my x? Our x would be this distance from origin. If you draw a perpendicular line onto x-axis, so this distance on x-axis, this would be the distance x, and this would be equal to r cos theta, because this angle is 90 degree using the trigonometry, and this distance, the y distance, this would be equal to r sin theta. So we have x as r cos theta and y as r sin theta. So this is the position vector associated with the bead. Now we have to calculate the velocity. That means we have to differentiate this r with respect to time. So here in the first term, because r is a function of t, and because r is changing with respect to time, the bead can move up and down this rod, and theta, it is also changing because the rod is continuously moving in a circular path like this. So this is also dependent upon time. So we have to apply the product rule to take the derivative. So we'll first take the derivative of r, that would be r dot, and cos theta as such, and then we'll keep r as such, and then we take the derivative of cos theta, that would be minus sin theta into the derivative of theta, that would be theta dot, into I cap as such. Again we have to apply the product rule over here, so we get this quantity. So now v square would be v dot with v. That means we are to take the dot product of v with itself. If you take the dot product, and if you remember the rules, that would be the dot product of I cap vector with I cap is equal to 1. That means a vector with itself, its dot product is equal to 1. Moreover, if it is a unit vector and two orthogonal vectors, because this I cap and j cap, they are perpendicular to each other, therefore the dot product is equal to 0. So by virtue of that, we have the square of this term, because I into I would be this thing and j into j would be this thing, the square of this term. When you evaluate and solve this out, you will only be left with v square as r dot square plus r square theta dot square. So this is the expression for v square. Now as we have v square, therefore we can evaluate t. Our t was half mv square, therefore substituting the value of v over here as this one, we have t as this. The next step would be to calculate the potential energy. But notice that here in the question we are given the wire is rotating in a force free space. That means it has something to do with it. Force free space means no force is associated with the given system. That means we can use this form of Lagrange equation. Del T by del Qj minus ddt of del T by del Qj dot minus is equal to minus Q, capital Qj, where what is this? This is the generalized force. And this is true for any kind of system, whether it is conservative, non-conservative. So notice we do not have to calculate this potential energy over here. We only require the kinetic energy over here. If you are not sure how this formula came up, you can visit the previous videos. I've explained this formula there in detail. So this is the Lagrange equation that we shall use, and in our question we are given force free system. That means our Qj would be equal to 0. So this right hand side, that would be equal to 0. So we are only left with these equations. Because our generalized coordinates, they are theta and r. First is r and second is theta. Therefore we have corresponding two Lagrange equations. One is this and another is this. And the right hand side is equal to 0 because it is given to be a force free space. So now we have t, so we can differentiate it partially with respect to r, with respect to r dot, with respect to theta, and with respect to theta dot. I think that is okay. So we can substitute these values over here, and you see in the solving the second equation, we have theta dot is equal to constant, which was the given condition to us that the motion of the rod is uniform, because the angular velocity over here, that is equal to constant. So now solving the second equation, substituting the values, taking the derivative over here, we have something like this. Now mass, because this is non-zero, therefore this term has to be 0. So and moreover, we have just calculated that, or it is given in the question that theta dot is equal to omega. Therefore we can substitute omega over here in place of theta dot. So it would be r double dot minus r omega square. This is equal to 0. So in our case, this is the equation of motion. Moreover, if you note that this is also the condition for centripetal force. So that means the motion over here is the outward motion, and which is by virtue of centripetal force, as the rod is rotating in a circular motion. So, well, that is it for this video. I see you in the next videos.